because the lines don't cross at all. Anyway, if you work at it a bit, I won't take the time right now, but if you work at it a bit, this identity is so strong that it tells you what happens if you either cross a knot through another knot or else remove a crossing. And after a little while, you find that you can calculate the J number for every knot. Actually, the easy part is to show that you can calculate J for any knot given our rule. The hard part is to show that there's never a contradiction. There might be a contradiction because there are many ways to apply the rule. This particular knot had about 15 crossings, and so we could apply our rule at any crossing, and then at any other crossing, and so on. There are many ways we could proceed, and you might run into a contradiction. But Jones and other knot theorists showed in the 1980s that there's never a contradiction. One always arrives at the same number, same answer for the Jones number, jk of a knot k, no matter how you calculate it. So the proof showed that Jones's recipe is correct, but it left a why question. Why it works, what it means if you wish. The trouble is that although that's sort of one of the most basic questions in math or physics, it's hard to explain if you don't work in mathematics or an allied field. If you're not accustomed to mathematical work, you might have only a hazy idea that there's a difference from understanding what's true and understanding why it's true. But the beauty of the why answers is actually a lot of the reason that people do mathematics in the first place. Now, in this case, as people worked on the Jones polynomial, they discovered more and more remarkable formulas with less and less understanding of what they meant. But there was a clue. In fact, there were lots of clues. As the subject developed, it had many ties with mathematical physics. In fact, Jones, in his original work, had one relationship to mathematical physics, and many others were discovered. A flood of things. Bewilderingly many ties between the Jones polynomial and mathematical physics. If anything, there were too many links between the Jones polynomial and mathematical physics. If you're trying to solve a mystery, it's much better to have a good clue than a large assortment of clues of dubious merit. So I won't try to tell in detail how this story unfolded in the 80s, but I will mention those who influenced me the most were three members of the IAS, one of whom is now my colleague on the faculty, and former Institute professor Michael Atiyah, the distinguished mathematician, who's now in Edinburgh. So there were all kinds of links between the Jones polynomial and mathematical physics of different kinds, but it turned out that the natural explanation has to do with quantum theory. So now I need to tell you a little bit about quantum theory and how it differs from pre-20th century physics. So imagine a classical particle. For example, it could be the planet Venus. It starts somewhere, it ends somewhere else. In between, it will travel on a nice, reasonable orbit that you can find by solving Newton's laws, by solving Newton's equations of motion. Here instead is a quantum particle. It can follow any path at all. A fairly typical path might be quite irregular, like this one. If you look in detail at the path followed by a quantum particle, it might look like it lacks rhyme or reason. Now, for the quantum particle, we have to allow all possible paths. I drew one here, but I drew three more over here. So these are paths a particle could follow in going from here to here. According to Feynman, it could do whatever it wants, so to speak. It can go on any path at all. I've drawn this path, this one, and this one. And since the lecture is about knots, I couldn't resist that two of my three paths are knotted. Although to make it easily drawable, I use the same knot in each case. This particular knot is called the trefoil. By the way, this knot is a little bit, as drawn here, it's a little bit more like a knot in real life. It starts somewhere and it ends somewhere else. It's tied down at the ends and it's knotted in between. It's not a freely floating knot in empty space like the mathematicians usually think about, and like I drew earlier. Now, one important thing is that we're doing quantum physics, but it's going to be relativistic quantum physics, because after all, the 20th century gave us relativity along with quantum mechanics. So when I draw a path, it's not a path in space, it's a path in space-time. So it's true that a path can be knotted, but that's special to 3 dimensions. If you had a 4th dimension, you could always slip the loops across each other. And in 2 dimensions, you couldn't even draw a knot. The lines would cross rather than avoiding each other in 3 space. 3 is the right dimension for knots. So if you're going to interpret your knots as the paths followed by a particle in space and time, it'll have to be a space-time of the right dimension. When we count time as one of the space-time dimensions, the real world has 4 dimensions, 3 space dimensions and 1 dimension of time. But to understand knot theory, at least in the approach I'll be explaining for the next little bit, we're going to imagine living in a world of only 3 space-time dimensions, not 4. A world of 2 space dimensions and 1 time. So this is actually what I drew. The world of 3 space-time dimensions, where you can think of time as running from left to right. And yes, we're letting our particles zigzag back and forth in time, since we allow that relativistically. So now I've drawn a knotted path. So a quantum physicist a classical physicist finds the right orbit by solving Newton's laws. But a quantum physicist doesn't know what the right orbit was. The quantum particle could travel on any possible orbit, and a quantum physicist has to sum over all possible paths by which the particle might reach its destination. How to do this sum? Well, this is a very schematic history of physics in one sentence, but roughly speaking, how to do this sum is what physicists learned in developing quantum theory and ultimately constructing what's now the standard model of particle physics. Quantum mechanically, any path is possible. But if the particle did travel on a particular path, which I'll call k, then there's what's called a probability amplitude for the particle to arrive at its destination via this path, and that amplitude depends on k. The way that the probability amplitude depends on k is very important. It's the reason that there's some order even in a quantum universe. All paths are possible, but peculiar paths with a lot of zigzags are not very likely. The particle could do anything, but when you do the sum over all possible paths, you get an answer that mostly, at least under familiar conditions where our ordinary intuition applies, the sum over all possible paths mostly corresponds to paths that are pretty close to the classical path that Newton would have favored. Now, but even to try to do this, to do the sum over paths and find out that Newton's result is a good approximation, you need to be able to calculate the quantum mechanical amplitude that the particle did travel on a given path k. That amplitude is given by something which is called the Wilson operator. I'll call it W sub k. For today, we don't really need to know exactly how it's defined. All we need to know is that it's a basic ingredient in quantum physics. And for instance, if you want to calculate the force between 2 quarks in an atomic nucleus, what you use is the Wilson operator. So once you start thinking about the sum over quantum paths and the Wilson operator, it turns out that there's a very simple connection between the Jones polynomial and quantum physics. The connection is simply the following. We regard a knot k as the space-time orbit of a charged particle. Then the Jones polynomial, in other words, Jones's number, is the average value of the Wilson operator. Here's the formula in its simplest terms. The number, J sub k, that Jones attached to a knot is the average value of the Wilson operator, where the averaging is a process of quantum averaging. You might wonder, what are the numbers 2, 3, and 5 that we used when we played the game? Well, they're determined by the charge of the particle and Planck's constant, loosely speaking. Now, one point I perhaps should add is that technically when we carry out this program, well, we don't use the standard model of particle physics. For one reason, we need a 3-dimensional model, not a 4-dimensional model. The model we have to use is developed using something called the Chern-Simons function for gauge fields, where Chern was one of the most famous mathematicians of the 20th century. Simons is also a very distinguished mathematician, as well as a businessman and IAS trustee. Now, why have I been telling you these things? Well, one reason is that I like them, and it's fun to relive my early days at the IAS. But that's not the only reason. There's actually a more contemporary twist in the story. I've been working on it this year, and I want to tell you at least a few words about it. Although it is a little bit harder to explain properly than the story we've just been talking about. So we took what you might have thought was a roundabout interpretation of knots. In everyday life, the simplest interpretation of a knot is an object that exists in space, an object in real space that we can see. But to interpret the Jones polynomial in quantum theory, we instead had to view a knot as a path in space-time. So interpreting a knot as a path in space-time is maybe less obvious than interpreting a knot as a physical object in space. Around 1990, when he was a member at the IAS, my colleague Igor Frankl started to develop pieces of what he hoped would be a new mathematical theory in which the knot would be seen as a physical object rather than a path in spacetime. I talked to him a lot about his ideas when he was here, and I wish I could claim that I encouraged him and made useful comments. But I didn't. I only gave him reasons it wouldn't work. Anyway, if it was going to work, it was supposed to involve a more powerful version of the Jones polynomial in a theory that would have one dimension more. Technically, the reason I thought it wouldn't work, actually, was that the Chern-Simons function is special to 3 dimensions. It can't be related classically to anything in 1 dimension more. So I thought that would mean that there wouldn't be a 4-dimensional theory related to the Jones polynomial, but with the knot as a physical object rather than a path in spacetime. But Frankl didn't listen, and he continued developing the ideas with colleagues such as Lou Crane, who's now at the University of Kansas, and his student, Michael Kovanov. And finally, by 2000, Kovanov created what's now known as Kovanov homology, which is a refinement of the Jones polynomial in which the knot is a physical object rather than the path of a point particle. Now, in a couple of ways, it's like the Jones polynomial. It's very clever to invent it, but once it's invented, it can be computed by an explicit set of rules. The only trouble is that I won't tell you the rules for defining Kovanov homology. For the Jones polynomial, I basically explained the rules, but maybe I went through it too fast. But for Kovanov homology, you really wouldn't want to go into a high school class and try to explain the rules for defining Kovanov homology. In principle, they're elementary, but it would take a pretty unusual high school student who would have the patience to try to understand it. You don't need quantum physics to define and calculate Kovanov homology, and in fact, most people working on it don't think in terms of quantum physics at all. But just like I told you earlier about the Jones polynomial, the literature on Kovanov homology is full of what answers, and it's kind of short on why answers. So there are amazing discoveries of what's true. They generate more and more mysterious formulas. And the possibility is open, or given the history with the Jones polynomial and the way that the Kovanov theory was invented as a more refined contemporary counterpart, you would at least wonder that maybe a quantum dimension is needed to get a better explanation of what the formulas mean. I think I told you this already. We can define Kovanov homology by an explicit recipe.